And everybody's checked in. Everybody's good? Yes. Okay. Uh, okay. I guess we should start at the beginning just to make sure everybody's on the same page on certain things, including measurements. So we'll start with this, right? We'll start a little bit about measurements. And before we really get to measurements, when we do take a measurement, right, it's really important to have both a number and a unit. Yeah, and units seem to always get lost along the way as people do things. And it's a really important part of a measurement because it tells people basically what that number represents. If I have 100, right, and I ask you, what do I have 100 of? You're going to say, I have no idea what you have 100 of because it just says 100. That could be $100, which is great. Yeah. Could be 100 pennies, still good, I think. 100 apples, maybe you like apples, going to make some apple pie. That's all good. So a number by itself is pretty much worthless, right? So you must always make sure that you have the units as you learn in Chem 50 and 40 as well. There's two types of units, right? There's like the English, or sometimes referred to as the US units, and there's pretty much what everybody else uses, which is the metric system. And in 1960, right, they came together and made some units that we typically use in chemistry and science, which are sometimes referred to as the SI unit, or the International System of Units. And let's be honest, it's really the metric system. So the metric system sort of one there. And you want to make sure that you use appropriate units along the way. There are crossover units that happen, right, between English and metric, but you definitely want to make sure you always have the proper unit along with the number. Also, really important to make sure that you understand what that unit represents, right? So if you have something like grams, that's a mass, right, versus milliliters, which is a volume. So understanding again what those different units represent in terms of the quantity of what you're measuring is really, really important. Speaking of measurements, since we are in lab here, whenever you do take a measurement, there's always some degree of uncertainty with that measurement. And that degree of uncertainty does depend on the type of equipment that you're using, or the piece of equipment that you're using. So for example, if we were going to use like a ruler, and we'll go this way. And say we want to measure like this guy, right? So whatever piece of equipment that you're using, you should always look at the scale and try to figure out how far you could take the readings to. And usually when you look at any type of scale on a piece of equipment, there's usually two types of markings that you see. There's usually the larger markings, which actually have numbers next to them. So in this example here, that's a 1, that's a 2. So our large markings here represent 1 centimeter. We also want to look at the smaller markings, which are usually the markings between the two big sort of markings. Remember that when you start counting the smaller markings, you always start past the last large marking. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So if I have 10 markings between a difference of 1 centimeter, each small marking represents how much? Oh, we have to take a field trip to Chem 50. It's right next door. Come on. 1 divided by 10 is 0.1 centimeters. Yes. So if you take that and divide it by 10, you get that. Yeah. So that means that each of these smaller markings here are 0.1 of a centimeter. That's 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2. Yeah. So whenever we take a reading, there should be certain numbers that no matter who looks at it, everybody should agree it is at least that much of it. So my little arrow here, everybody should probably agree it is at least 1.4. So we would record 1.4. These are sometimes referred to as all the certain numbers. Now we could clearly see that my arrow doesn't stop at 1.4. It's not quite 1.5. And that is where really the estimation or uncertainty is going to come into play in this case. I may look at it and go, I feel it's like halfway between those two markings. Somebody else may look at it and go, I think it's a little less than half. Maybe it's like, only halfway, a little bit less than that. So I may record a 5. Somebody else may record a 4. Somebody may look at it and go, it's a little bit more than half, maybe, or something like that. And obviously, we would record our units with this. This number here is what is sometimes referred to as the first uncertain digit or number. And when you do take a measurement, you should always record all the certain values plus that first uncertain number. And when you do that, by the way, that makes up what? That makes up everybody's favorite thing, significant figures. Yeah. That is basically what significant figures are in a measurement. When you take all the certain numbers plus that first uncertain number. By the way, that would mean this value here has how many significant figures? 3, right? Yeah, so it has 3 significant figures in this case. Now, it does depend on the scaling that you're using and the equipment that you're using. For example, if we had something that looked like this, like maybe a graduated cylinder drawn really badly. Yeah, it's not too bad, I guess. And 30 there. Call this milliliters. We'll throw some liquid in there. Right. So in this particular case, right, we have a liquid in a glass container. By the way, when we put a liquid in a glass container, typically we'll do this move, right? That is known as the meniscus, yeah. And we typically read from the bottom of the meniscus, right? Why does that happen, by the way? Yeah, so it's a couple of things, and including in it is the attractive forces between the liquid and the walls of the glass are actually stronger than the attractive forces between the liquid and itself. So on the side where it comes in contact with the glass, it starts rising through capillary action and makes that sort of U shape typically. And that's why we read from the bottom of the meniscus, because that's truly where the volume is if it didn't have that attracted force, right? And there's no contact there. So that's really where it is. So we typically read from the bottom of the meniscus. There are some things that will actually do a meniscus the opposite way, right? And you would read from the top of the meniscus, something like mercury, for example. The attractive force between mercury and itself is actually stronger than that between mercury and the glass, so it actually comes in on itself and makes a sort of reverse one. Since they take mercury out of most chemistry labs, you probably won't see too much of that. So most of the time, our meniscus will kind of be this U-shaped type meniscus. But here, if we look at the markings, our large marking in this case is 10 milliliters. Once again, if we count our markings from the past the last one to the next one, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 in this case. So in this case, each of our small markings represents how much? 10 divided by 10 is 1 milliliter, right? So that's like a 21, a 22, a 23, 24, 25, 26, 27, 28, 29, and 30 going upwards. So if we take a little bottom of the meniscus action here-ish, drawn semi-crooked, we could see that it is at least 26, which is what we would want to record. Not exactly 26, but maybe you don't feel that's exactly halfway, so maybe you do a 4 and a milliliter. This would be our certain numbers. This would be our uncertain number, our estimated digit. And again, this guy would have 3 significant figures in this case. They would all be significant. Basically, what we're saying is I think it's 26.4, but maybe it's like 26.5, maybe it's 26.3. Usually plus or minus 1-ish of that last digit is typically what we're kind of saying when we take a measurement like this. Question on that there. So it does matter as well, right? Your scale, because you could have something, say, like this, even worsely drawn graduated cylinder. You'll find out why I failed art 9 times. It's all right. There you go. It's not for everybody, art. There you go. So if we got something like this in this particular case, our large markings again here are 20 and 30, and that is 10 milliliters. In this particular case, we got 1, 2, 3, 4, and 5 markings. That means each of the smaller markings represents how much? It does represent 2 milliliters, right? That means that's like a 22, that's a 24, that's a 26, that's a 28. So when I take my reading right about here, between 26 and 24 is which number? 25 is the best you could do on this case. That would have how many significant figures? Would have 2 significant figures. The uncertain digit is which number? Is the 5, yeah? And that is where, we're saying there is no way good in that sort of scale to figure out where 24 stops and 25 starts, right? So there's no way to do that. On the previous ones, it was just like 1 digit sort of difference. So you could kind of go halfway there is halfway to the next number. But on this one, you can't do that because of the scale that's there. So it's really important to make sure that you do look at the scale, what you're using, even if it is the same as the person next to you. It might have been made by somebody different and have a different scale on it. So you always want to make sure that you look at it. When you have a digital reading, should you record all the numbers or just part of them? You should record all of them. If it's digital, then it's important. Otherwise, it wouldn't be on the display. So you should always record all of those numbers. Now, typically speaking, you could go one more place to the right of the smallest marking. Not in this case, but here the smallest marking was 1 milliliter. We were able to go one more place to the right to take our reading. And here the smallest marking was 0.1. We could go one more place to the right to take our reading. By the way, if you're not sure how far you should take a reading of something, but you are sure of what the smallest markings represent, you could just divide the smallest markings by 2. So for example, if I take 0.1 divided by 2, that's 0.05 centimeters. That's like plus or minus 0.05 centimeters. But really, you can look at it and go, I should take it to 2 decimal places. You take this one and divide it by 2, that's 0.5 milliliters. I should take it to 1 decimal place. Even on this one, if you divide it by 2, you get 1 milliliter, which means I should take it to the whole number. So if you're not sure, but you are sort of confident of what each of the smallest markings represent, you can just take the smallest marking divided by 2, and that will basically tell you, how far you should take the reading. Any questions on how to take proper readings? You do need to be able to do that properly when you write things in your lab notebook and such. They do need to be the proper number of significant figures and digits based on the equipment that you're using. So make sure you keep that in mind. Speaking of sig figs here, our normal sort of quick sig fig conversation. Significant figures. These are typically measured values, right? And all non-zeros are significant, right? So if I had 2, 4, 5, that should be 3 significant figures. When we count significant figures, we always go left to right, and we start at the first non-zero. It's basically where we start counting. Zeros, right? If we have zeros that are referred to as leading zeros, they are not significant. So if we had something like 0.003234, we wouldn't count any of these. This is where our first non-zero. That is where we should start counting, and the rest of them are non-zero. So this would have 4 significant figures in this particular case. We also could have some zeros that are trapped, and those are significant. So sometimes we call it captive zeros as well. So 4004, we would start counting here. These are trapped, makes them significant, and that is a non-zero, which means that would be 4 significant figures in that particular case. Any questions on that there? Now, the 0 at the end, trailing zeros, are the ones that give people the hardest time. they are significant if there is a decimal place, right? Or point in the number. It doesn't have to be right next to those zeros, but as long as it's anywhere in that number, it makes the zeros that come at the end significant. So if I had 600 like this, how many significant figures? As one, right? And that is that. If I wrote 600 like this, does have three significant figures, and my 0, 0, 0, 0, 4, 0, 0, 3, 0, 0, 0 has how many? I have no idea. I was just writing numbers. So we would start counting here at 4. These would be traps, so they're significant. That would be significant. These 3 zeros at the end would be significant because of the decimal point in there. So I'm sure you counted right there. 1, 2, 3, 4, 5, 6, 7 in this case. Yeah. Question on how to count significant figures. By the way, going back to our measurements before I move too far from that, what happens if we take this guy here and we're measuring this right on the 1.4 mark? Should I record 1.4 centimeters, 1.40 centimeters? Is there a difference? There is a difference, right? And the difference is actually with the significant figures. Top guy has how many significant figures? 2. The uncertain or estimated digit is the 4, right? That means you're saying, I think it's 1.4, but maybe it's 1.5, maybe it's like 1.3. And as we could clearly see, that's a pretty big area of error, right? And uncertainty. When we actually could take it to this, which means it's 1.40, maybe it's 1.41, 1.39. That's like right about there, right? Much smaller degree of error. So sometimes when people do take measurements and magically everything is like perfectly on lines, I love that. It's like, I sat there at the balance and got it to exactly 52.0000. Yeah, good luck with that. If it is right on the line, you do have to keep the 0 to maintain the proper number of significant figures, because if you drop the 0, you pretty much made your measurement pretty crappy in that sense, a lot crappier than it should be based on the scale that's there. So do not get rid of significant figures and put zeros in that you need to. Also, you should not add zeros if you shouldn't, right? Because that makes your measurement better than perhaps it should be as well. All right, so I want to make sure I covered that there. Let's talk a little bit more about significant figures and more so calculations, right? So when we have significant figures in calculations, we typically do one of two sort of things. We will typically either multiply or divide. And when we multiply or divide, we are looking at the answer should have the same number of significant figures as the number with the least number of significant figures. So when you multiply or divide, you're looking at significant figures. So if you took 4.25 times 1.2, this has 3 significant figures. This has 2 significant figures. That means that my answer should have 2 significant figures when it's all said and done. Same thing if you're dividing. If you're adding or subtracting, you're looking at decimal places. And your answer should have the same number of decimal places as the number with the least number of decimal places. So if I take 1.256 and add it to 3.4 and add it to 2.04, it's a lot of math there. I'm going to try it. 6, that's like a 9, I think. That's like a 6 as well, maybe a 5 and a 6. Hope for the best there. I think I got it lined up there, right? All right, so when we look at this, we got 3 decimal places. We got 1 decimal place. We have 2 decimal places. Our answer should come here to 2 decimal places. I should look to the number to the right. It means 6.7, right, is where we should end up with at this point. 6.7 has 1 decimal place, but how many significant figures? Has 2, which could be important if you then take that number and do something like multiplying and dividing. So if you're doing a number of steps together, you do want to keep track of your significant figures. So if you're taking like multiplying things and then maybe dividing, here we would be multiplying. That would be 2 significant figures times 4 significant figures up on top, which means really we should end up with 2 significant figures up on top, which we are then going to divide by how many significant figures here? 5, as a 0 is not significant, right? There's no decimal, which means we should end up in this case with 2 sig figs. Normal rules of rounding apply, which means you really shouldn't round to the end usually in most cases, but you should keep track of your significant figures and all that as you go through your calculations and then kind of clean it up at the end. The reason you don't want to round too much along the way is if you do a calculation, get an answer, then take that number, do another one, get an answer. And if you keep rounding at every point, you probably will be moving yourself further and further away from the correct answer. So try not to round too much. Some people call it guard digits or keep a few extra numbers or I don't know, whatever you like to do. But try not to do any of that crazy rounding. Also, speaking of rounding, if I had 13,333 and I wanted 2 significant figures, what should the answer be? Should be 13,000, right? Should it be 13? Should not. This does have 2 significant figures, but there's a very big difference in the meaning of those 2 numbers. A good way to remember it is to think about money. Somebody owed you $13,333 and they said, I pay you 2 significant figures. Here's $13. You're not going to be very happy with them, I imagine, right? But if they give you 13 grand, maybe you'd be happy just to see the 13 grand come through the door, right? Maybe you gave them like a $333 discount or whatever it may be. So sometimes people try to go crazy with the sig figs in terms of trying to get the right number of sig figs, that they kind of go crazy on the rounding, and you never want to round that changes really the meaning of the number along the way. Any questions on any of that there? Speaking of some of this stuff as well, let's talk a little bit about scientific notation. Yes. Scientific notation, if done correctly, should look like this: n times 10 to the n. That is a number between 1 and 10. So it should not be 10, should not be 20, should not be 100. It needs to be less than 10. 1 is okay, but it cannot be less than 1 either. Times 10 to the little n, which may be positive or negative, depending on which way you need to move the decimal point to get yourself to a number between 1 and 10. So if we had 42,560, and we would assume it's here and go 1, 2, 3, 4 places, 4.256 times 10 to the 4th. If it's a large number, you have a positive exponent, right? And or if you move it to the left. If you have a smaller number, 0.003240, we would go 1, 2, 3 places to the right. 3.240 times 10 to the minus 3. Now, why did I get rid of the 0 here and not here? When you write a number in scientific notation, right? All of the numbers that come before the times 10 part are significant, right? So all those are significant, which means, as you correctly said there, when we look at this, we really only have 4 significant figures, as that 0 is not significant in the first number. So when I write it like this, all 4 of those guys are significant, and that would give me 4 significant figures. Same thing here. This 0 is going to be significant because of the decimal point. That means I really have 4 significant figures here as well, which is why I did keep the 0 in this case. and I will have 4 significant figures. So you should never lose significant figures as you go from decimal form to scientific notation or back and forth. Um, sometimes the only way to get the proper number of significant figures is to write your answer in scientific notation. So for example, if I had 12,235 and I wanted, say, 3 significant figures here, right? We could write it like this, which would be 12,200. We could also write it as 1.22 times 10 to the 1, 2, 3, 4. And that would give me my 3 significant figures. But let's just say I wanted only 2 significant figures. I could write 1.2 times 10 to the 4th. And now I have 2. Let's say I just needed 1 significant figure. 1 times 10 to the 4th would give me 1 significant figure. So because you could kind of control how many significant figures you need, sometimes the only way to get it to the right number of significant figures is to use scientific notation. Do you have to use scientific notation on everything that you write in this particular class? You do not, but you might need to do it in certain cases. But you should try to get everything, obviously, to the proper number of sig figs and all that kind of stuff when you're doing calculations. I probably not going to be too concerned, significant figures. But if it is a big problem, you will lose points. So you should try to get everything to the proper number of significant figures. But if you miss it by 1 and only a couple of places, you'll probably be okay. Probably more concerned in this class about the calculation part. But if you give me like 500 significant figures, you're going to lose points. So you should try to aim for the right one. You should always try to give it to the right number of significant figures when you do give answers and stuff like that. So, all right. More importantly, though, in terms of scientific notation, than being able to obviously write it in scientific notation and as a decimal is what most people don't know how to properly do, which is actually use your calculator and scientific notation. So hopefully it's a review for you, but let's just make sure everybody understands how to properly use your calculator and scientific notation. On everybody's calculator, you should really have a dedicated exponent button. And on most people's calculators, there's usually 3 different types. There are 4 nowadays, but I guess 3 mainly. You should have an EE button. You should have an EXP button. And if you have maybe some of the newer type calculators, you may have this type of setup, which is you may actually have a button that says times 10 to the n. And usually if you have that, you'll have like a wheel on your calculator. And a lot of times these are like 2-tone type calculators, like there's a main color and the sides are different colors and stuff like that. So if you have those buttons, we'll talk about what you need to do in just a second. If you have the other 2 buttons, you could pretty much do what we're going to talk about here. So if we're going to enter some things in scientific notation to our calculator, by the way, you should also have a negative button, which usually looks something like this or like this on your calculator. Is your negative button, not the subtract button. So if you have something like 4.25 times 10 to the minus 6 and you want to properly punch that into your calculator, you should hit 4.25. You should hit your exponent button. So I'm going to talk about these 2 buttons first. And when you do that on your calculator, you'll either have 4.25, we'll put an E, or maybe you'll have a calculator that will pop up a couple of zeros up on top, may even say times 10 on the bottom, but it'll pop up those zeros. Is typically when you do that. When you hit the exponent button, by the way, it represents this part of the number, the times 10 part, which means you should not be hitting the multiplication button. You should not be doing anything like shift log or inverse log or anything like that. What is left is at this point, you would hit the negative button and it'll pop a negative in there. And then you hit 6, it'll pop a 6 and turn that into a 6. And now that is what it should look like properly if you use your exponent correctly. And I would definitely tell you, you want to make sure you're using your exponent correctly in this class. Otherwise, you will be off. Usually, you know you're punching it in incorrectly when you look at the answer and it's like, wow, that's pretty close, but the exponent part's kind of off by 1 or so. That's usually you're typing it in incorrectly. Now, if you happen to have this two-tone sort of set up here, you got to do a couple of other things the way that calculator is sort of programmed. You need to open up with the parentheses and then go 4.25 and then hit that button. And what it will look like on your calculator is a parentheses 4.25. It will slap in there times 10. You'll have a little blinking cursor right there up on top. At that point, you could kind of do the rest of it. You would hit your negative button and 6. And when you do that, it will look like this. It will put the -6, and now you will have your little blinking cursor to the right of the 6 up on top. And that's usually a problem for those type of calculators. So that is where the wheel comes into play. You're going to hit the right-hand side of the wheel at this point, and that's going to bring your cursor down to a normal cursor. Now you have like a normal cursor. Now you can close the parentheses, and you will have something that looks like this. And you need to do that for every number that you put in scientific notation if you have that type of calculator. Otherwise, if you do not put the parentheses there, it breaks up your number incorrectly, and it usually will do the math wrong, and you'll get the wrong answer. So probably more important than everything else is that part of how to use your calculators where people screw up on the most. And that's really important to be able to punch these things in correctly in your calculator. Now, if you have either of these two buttons, you don't have to be super careful. You can pretty much don't need parentheses or anything like that, and you'll be okay. Any questions on that there? Okay, so just to try one, if we had 4.25 times 10 to the minus 11, and we wanted to divide it by 6.2 times 10, we'll go 24. See what you get, punch it in, make sure you get the right answer. I'll do it as well. Okay, so again, if I was punching this in, a little 4.25 exponent button, negative button, and 11, little divide button, 6.2 exponent button. This is a positive exponent, which means you just put 24 and hit equals. On my display, I got on my calculator 6.8548337. 8387. 1e minus 36. Yeah, something like that. So a couple of things. When you are given an answer like that, you don't want to forget the back part here of your number. By the way, sig figs, we should end up with how much? Should end up with 2 sig figs. That is 3 significant figures, right? That is 2 significant figures, which means we need to do a little bit of rounding. 6.9 times 10 to the minus 36. Yeah. You don't want to forget this part. When you do write an answer in scientific notation, you should write it as times 10, not E. So don't use E on your things. You should write it as times 10 when you write it. Question on that one there. Clear if you have the other calculator, you got to put parentheses around each of those numbers like we just talked about, and you should get the same answer. Any questions on how to use your calculator for exponents and scientific notation? If you're not sure where your exponent button is, still at some point, come see me. We'll find it. Yeah, and you'll hopefully be able to use it. Before we kind of move on from measurements and all that, right, there is a difference, right, between accuracy and precision, right? Accuracy is how close you are to the true value, right? Precision is how close a set of numbers are to themselves. We'll do the classic example everybody uses, which is let's throw some darts in a bullseye, right? Goal here is to get the bullseye. So I throw my darts, right? Missed the board. Sad. Over there, missed the board twice. That's even worse. Am I precise? Am I accurate? No, and hopefully nobody's standing next to the board because that's going to be a mess. All right, so I pick up my darts and maybe my pride, and I throw them again, and I go boom, boom, and boom. Am I precise? Am I accurate? I'm precisely not accurate, right? Yeah. This brings up a really good point. You can be very precise when you're doing things since we're in the laboratory, right? You could do the experiment wrong every time the same way wrong, but it's still wrong, right? So you can mess up the same way every time and be very precise in the way you're messing up and still not be very accurate to what you're looking for, which is typically not what we want to do. Pick up my darts here, right? And I throw them again. And now I hit boom, boom, boom. Am I precise? Am I accurate? I'm precisely accurate in this case. And that's really what we are trying to do when we do experiments, right? We want to be accurate. We want to be close to what the true value is. If we know it, we also want to be precise. That is why in experiments, we typically do trials more than once, right? We do things multiple times. And that's to see if something is repeatable. And that's what precision looks like. We do calculations sometimes to help us decide what's going on in each of these. Usually we do a little percent error, right, on an accuracy. We take our experimental value minus our true value divided by our true value times it by 100. Do I want a high or low percent error? Low is good, right? High is like, you kind of screwed up, right? Precision, we look at something like deviation, like standard deviation, percent standard deviation, and we see how close the numbers are to one another. So those are a couple of things that we look at. Any questions on that there? Okay, then let's get into some other things here, perhaps. Let's talk a little bit about molar mass. Yeah, the units of molar mass. Where are the units of molar mass? That is grams per mole. I was getting worried. It got silent there for a second. Make sure we're in the same place. So grams per mole is the unit of molar mass. We typically can calculate the molar mass of a substance by going to the periodic table and taking the number on the bottom, right? That is the molar mass. If it's grams per mole, that's the atomic mass. If it's AMU per atom, but that is the molar mass. We typically take 4 significant figures, right, when we pull it off the periodic table. And the molar mass is really your conversion factor, right, to go from grams to moles and moles back to grams. That is the molar mass, right? If I wanted to go to atoms or molecules, whose number should I use? Avogadro's number. Avogadro's number sounds good. Uh, Good news is we don't use it very much in this class, but that is what we use as we go from molecules to atoms and back to moles and stuff like that. Molar mass, though, we do use a lot in here. So, for example, if we had the molar mass of, say, CH4 we wanted to calculate, we would go to the periodic table, right, add up all of our parts here. And basically here we would have 12.01 grams per mole for our carbon. We would add it to 4 times 1.008 grams per mole for our hydrogen. And again, that will give us a molar mass here of 17.3, I think, or 1604 in this case. 16.04 grams per mole. Now, when we do calculations, right, and let's just say we had 62.5 moles of CH4 and we wanted grams, we can calculate it using the molar mass. We could use the molar mass like a conversion factor, right? You could say there are 1604 grams over a mole, or you could flip it around and do a mole is 16.04 grams. We use conversion factors because when we show calculations in chemistry, we do what is referred to as dimensional analysis, yes? They sometimes call it just problem solving, but it's really called dimensional analysis, where we use units to cancel things out, which is how you should show your work, right? When you do work here in chemistry. So we go 62.5 moles of CH4. And the nice thing about dimensional analysis is opposites cancel. So the moles are up on top. So to get rid of the moles, it needs to go in the opposite location. So we would use our conversion factor over here. And we would times our 62.5 times our 16.04. That's going to give me 1002.5 grams, as the moles on top and bottom cancel in this particular case. By the way, significant figure wise, where should I end up? Should end up at 3 significant figures, right? Can I write it as a decimal to 3 significant figures? No. So this would be a case where you got to go 1, 2, 3 and go 1.00 times 10 to the 3 grams in this case, right? Is 3 significant figures because that's like 4 basically, and that is 3 significant figures, right? So it is our least number, and we are multiplying or dividing when we do dimensional analysis. So we are looking at significant figures in this case. Any questions on that there? So you want to make sure that you use things and set things up with units so that you can see things canceling. Again, that's really important as well. Any questions on that there? All right. You will have to use the molar mass, for example, in labs as well, to figure out how many grams of stuff to weigh out and things like that. So, we see a lot. Let's then talk about some chemical equations, which is definitely part of this class that you need to be able to write. So let's just make sure we hit the basics here. Obviously, on the left-hand side of the arrow, they are called what? Reactants. Yeah. Right-hand side of the arrow are the products, right? And when we write formulas in an equation, we use the proper chemical formula. We also see sometimes states like S for solid, L for liquid, G for gas, AQ for aqueous, right? That's what that is. Environment. And when we use an equation, we also will sometimes see things written on top of the arrow. Sometimes catalysts are written up on top of the arrow. Catalysts are not reactants. They're not products. They do not get used up in a reaction. Most of the time, as we'll talk about, catalysts are there to make the reaction occur faster or speed up the reaction. So sometimes you'll see things like platinum, maybe H plus, it's an acid catalyst or something like that written. Other things you sometimes see on the arrow, right? The delta symbol means heat, yeah. And again, sometimes you may see up there water written, which means you took something and dissolved it in water. So those are also 2 things that you sometimes will see. Clearly, we should never use an equation unless it is balanced, right? So equations always has to be balanced. And that means that when we do have an equation, we only balance equations by changing the coefficients in front and never the subscripts. We never put numbers in between. So you always want to make sure that you only change those coefficients. When you properly balance an equation, all the numbers should be whole numbers, yes. They also should be the simplest set of whole numbers, which means that if you could go through all your coefficients and you could round them down or divide them down by a common number, you should do that. For example, again, if you end up with 2a plus 4b goes to 6c, We'll just say this is balanced. This would not be a properly balanced equation because you technically could go through and divide everybody by 2. And that would give you A plus 2B goes to 3C in this case, right? And that would be it. You obviously, as you probably learned as well, you could use a fraction to balance an equation, but you do need to clear it when it's all done. And you clear it by multiplying by the denominator in the bottom. We have balanced equations because in chemical reactions, what are the only things involved when you have a chemical reaction in terms of atoms? There's protons, electrons, and neutrons. Which ones are involved in chemical equations or reaction? It is just the electrons, right? In a chemical reaction, all you do is break all your bonds, which are electrons, and you make new bonds, which are also electrons. We never touch anything in the nucleus, which is where our protons will lie, right? Out of protons, electrons, and neutrons, which one is the most important in terms of the element? It is the proton. It is the atomic number that you find on the periodic table, wherever our periodic table is, right? That's the number above the symbol on the periodic table, right? Every element has its own atomic number or its own number of protons. So because chemical reactions don't involve anything involving the nucleus, it's only electrons. We always have the conservation of those elements, the law of conservation of mass, right? So if you start with 4 carbons, you should end with 4 carbons. They may be in different things. As we'll talk about when we hit nuclear chemistry, in nuclear chemistry, it's all about changing what's in the nucleus, protons, neutrons, and stuff like that. So we do not get the conservation of elements like we do in normal chemical reactions. So in nuclear reactions, we actually don't get that conservation of those elements. Any questions on there? Speaking of equations, right? We sometimes do calculations from equations. I believe they call that stoichiometry still, right? That is our mole to mole sort of relationship we got going on, right? We could get a mole to mole relationship from the coefficients in a balanced equation. We could say for every 1 mole of N2, we react it with 3 moles of H2. For every 1 mole of N2, we get 2 moles of NH3 out. For every 3 moles of H2, we get 2 moles of NH3. These are sometimes referred to as stoichiometrically equivalent to each other. And from each of these, you could write 2 conversion factors you might have learned. 1 mole of N2 over 3 moles of H2 are 3 moles of H2 over 1 mole of N2. And obviously, you could write 2 conversion factors for each of these guys as well. We do not use all the conversion factors in a stoichiometry problem, right? We use whichever one is most important to what we're doing. So for example, here, if we had, we produced 12 moles of NH3, and we wanted to know how many moles of N2 would that be? We could set it up again stoichiometry wise, 12 moles of NH3. We would use our relationship between NH3 and N2, and again, go opposite in this case. NH3 on the bottom, 2 moles of NH3, 1 mole of N2. Moles of NH3 would cancel, gives us 6 moles of N2 in this particular case, right? That would be how much we started with in this case, right? That would have been how much moles of N2 we would have needed in this reaction to produce those, whatever I made up there, 12 moles of NH3. By the way, if we start out with 2 moles of N2 and we want to know how many moles of NH3 we produce, we would do a similar thing. We would start with our 2 moles of N2. We would use our mole to mole relationship from the equation. 1 mole of N2 is 2 moles of NH3. That would give me 4 moles of NH3 that would be produced here. That would also be known as what? Starts with a T. And there's a Y in the end of their name. That is the theoretical yield. Yes, that is how much you produce from the equation based on how much you started with. That would be our theoretical yield in moles, which we could use the molar mass there that we had earlier, 1604, I think, grams. Actually, that was not this guy. It'd be 1703 grams per mole of NH3 in this case. That should be 1401 plus 3 times 1.08. 1703 grams per mole of NH3. The moles would cancel, and that will give us grams. That would be our theoretical yield, whatever we get there in grams. Theoretical yield, right, is your maximum yield that you could get. If everything went perfect based on the equation, the stoichiometry, there was no side reactions, you weren't a klutz and spilled everything right on the floor, that is how much you should produce. By the way, there's also other types of stoichiometry problems that you should be familiar with. Dare I say the words limiting reactants or reagents, whatever you want to call it. There's limiting reagents or reactants. There's also excess, right? Reagents or reactants. That is a situation that you need to calculate when you are given the starting amount of both reactants, right? Or you have enough information to calculate the moles of both reactants. That is how you know is a limiting reagent type problem. You're able to get the moles of each of the reactants. That means you have to do an extra step along the way in your calculation, depending on how you were taught, who you were taught by. There's like multiple ways that you could do those calculations. I would say nowadays people are taught just to do two separate calculations. Yeah. From each reactant to figure out how much product each one makes. Whichever one makes the smallest amount of product is your limiting reagent and your theoretical yield. Is that how most people are taught these days? There's also, you could do a stoichiometry calculation between both reactants to see if you have enough of one reactant to use up the other reactant. And you could do that as well. That was a popular one years ago. But nowadays, people just have you do two separate ones. And lastly, most people don't do it, but ice table type calculations, you could do that for limiting reagent type problems as well. Limiting reagent is the one that gets used up first. This one you have plenty of, and you have some left over at the end of the reaction. And that also is something you probably calculated in your limiting reagent type problems, how much of your excess reagent is left over at the end of the calculation you could do as well. Which one is the most important in terms of how much product you make? It is always the limiting, right, that determines how much product you produce. That is why when we do have limiting reagent problems, one of the first things you have to do is figure out which one is the limiting reagent, because it is that guy that determines how much product you make. The reason we don't have to do limiting reagent calculations, right, in a situation where we're just given one of the reactants, it's assumed in those cases that that guy is the limiting reagent and the other one's the excess reagent. So that's why we don't have to do it. But when you do have enough information for both reactants to get to moles, you do have to do that additional part of your calculation to figure out which one's your limiting reagent and which one's your excess reagent. Once you do that, we oftentimes are interested in what's referred to as the percent yield, right? Percent yield is the theoretical, is not, it is the actual yield divided by the theoretical yield times 100%, right? Now, the actual yield is pretty much in a lab, what you actually got when you did the experiment. In a book type problem, they give it to you. Usually they say, hey, you produce this much of it. Theoretical yield is a calculation that you do based on the equation and how much you're starting with, which gives you your maximum yield. You divide them both and you get a percent yield. Do we want low or high percent yield? High. Do we want over 100% yield? Is that good? It means that you screwed up somewhere, usually, right? A lot of times people can't get over 100% yield, but it usually means there is some type of error in your thing. For example, maybe you did a precipitation reaction and you collect the precipitate on filter paper, you filter it, and you don't let the filter paper dry, and you go reweigh it. And when you weigh it, you're going to get all that water weight as your product that you actually didn't produce, right? And that will get you obviously over 100% yield, which is not usually a good thing. So high yield is what we're looking for, percent yield, but not over 100. And again, percent yield and percent error are different. Don't confuse those two things. We typically use a lot of percent error in this class, a little bit of percent yield, but not very much along the way. Any questions on stoichiometry, equations, balancing equations? These are all things that you do need to be able to do. Yeah. All right, continuing our journey down memory lane of Chem 50 here, we're going to then talk about probably a really important thing for this class, which is types of reactions. Yeah. So as I mentioned before, it's really important for you to be able to, in this class, be able to write chemical equations and reactions correctly. It will help you with the calculation part. It's also required, by the way, that when you are given problems that have equations, you're expected to write the equations, not just like fake the math, like I said earlier. You need to write the equations and stuff like that. So as you perhaps remember, there is two main types of reactions that pretty much everybody falls underneath. There's kind of two big classification of reactions, and then you can classify reactions a more specific way. The one major type of reaction are double displacement reactions, which we see a lot in this class. And a reminder that double displacement reactions have this general setup where basically you are taking two ionic compounds, positive guy, positive guy, and a negative guy. And what happens in a double displacement reaction is the two positive guys switch partners. And you make on the product side two new ionic compounds along the way. So double displacement is sort of a big class of reactions where more specific types of reactions fall underneath. So when you do this little switcheroo here, perhaps one of these guys makes a solid. Yeah. Perhaps you make a solid in this case. That is what is sometimes more specifically called a precipitation reaction. And that is when you do this double displacement, like you take some sodium chloride plus some silver nitrate. These are both aqueous, right, which means they're solutions, positive, negative, positive, negative. Sodium ends up with the nitrate, silver ends up with the chloride, and we end up with a little sodium nitrate and silver chloride in this case, right? And of course, we remember our solubility rules, which there will be some solubility equilibrium that we will talk about. So if it's been a while for your solubility rules, you might want to refresh it along the way. Be very helpful when we get to the solubility sort of part of our talk. Nitrates and sodium are soluble in everything, right? There's no exceptions. So that's going to get the aqueous symbol, which means that you do not have a solid. Chlorides, bromides, iodides are soluble in everything except for three things: lead, mercury 1, and silver, right? Which means instead of it being soluble, this is going to be insoluble. This is what is sometimes referred to as a precipitate, abbreviated PPT for precipitate. This is a precipitation reaction. It really is a double displacement reaction, but more often referred to as a precipitation reaction. I'm going to do it here. Here we go. This is a molecular equation, right? When we have this type of reaction or other types of reactions, we could also write another equation that describes really what's happening, which is sometimes referred to as the total ionic equation or complete ionic equation, whichever one you maybe learned, or just ionic equation. We could break apart things that are strong electrolytes. Yes, strong electrolytes are things that go for a swim and break apart into ions, right? And they do what? What a bunch of ions in solution will do. They conduct electricity. Yeah, you put the light bulb and it goes on very, very brightly. So sodium chloride is a strong electrolyte, which means it will break apart into a sodium ion and a chloride ion. Silver nitrate, also a strong electrolyte, will break apart into a silver ion and a nitrate ion. And I'm just going to go underneath since I'm running out of room there. The sodium nitrate will also break apart into a sodium ion and nitrate. And our silver chloride, which is a solid, will stay together. This is what's referred to as a total ionic equation. This is really what's happening in the beaker when you throw all these things together. Ions are floating around, and the silver and the chloride are coming together to make silver chloride. From this equation, you should look on both sides of the arrow, and you should be able to find two, in a lot of cases, are ions that look exactly the same. So there's a sodium there and a sodium there. There's a nitrate on the left and a nitrate on the right. Those things that are the same ions on opposite sides of the arrow are called what? They are spectator ions, right? And much like the name implies, they're just hanging out watching, which means we typically cancel these guys out. And that leaves us our third type of equation, which is a silver ion that's floating around. We'll go find a chloride and we'll come together to make silver chloride solid. This is what is referred to as the net ionic equation, right? So I will say, as we go through the semester, we will write total ionic equations, net ionic equations along the way. So if it's been a while, you may want to review some of that there. Any questions on that? Now, in addition to precipitation reactions underneath double displacement reactions, another more specific classification falls under there, and also something that we deal a lot with in this class. So under double displacement reaction umbrella, you have acid-base reactions. So when you take an acid plus a base, you typically get two things. You get a salt and water. Yeah. Salt's an ionic compound, and water obviously is H2O. So if we take something like HCl, which is hydrochloric acid, react it with sodium hydroxide, which is a strong base. This is really a double displacement reaction because this is a positive, negative, positive, negative. The H and the OH comes together, and that is where we get our water from, right? And our sodium and our chloride come together, which is where we get our sodium chloride in this particular case. This also you could write a total ionic equation for. That's a strong electrolyte, which means it will break apart into H plus and Cl minus. That's also a strong electrolyte, which will break apart into sodium and hydroxide. Water, which is a pure liquid, will stay together. When we write these type of equations, right, we keep liquids together, we keep solids together, typically gases, and anything that's a weak electrolyte, right? A weak electrolyte is something that will break apart a little bit, but mainly stay together. So a lot of weak acids that we will deal with in this class are weak electrolytes, like something like hydrofluoric acid will mainly stay together in solution as an HF unit. And that's different than something like hydrochloric acid, which is a strong acid here. It will 100% break apart in solution. None of the HCl units will stay together. It'll all just be ions floating around, which is why it's a strong acid, versus something like hydrofluoric, which will basically stay together. In this case, it is the chloride on both sides as soon as I finish writing the rest of it here. And our chloride, there we go. Chloride and our sodium, which are spectator ions. And this is really the major change that's happening when you put together an acid and a base is the formation of water. As you may also remember, there's really three reasons why a reaction takes place. One of them is the formation of water. One of them is the formation of a solid. And those are two of the three reasons why a reaction actually takes place. So under double displacement reactions, which we see a lot in this class, especially the acid-base parts, we have more specific acid-base classification and precipitation classification. Any questions on that there? That leaves us the other big classification, which is the redox reactions. Redox stands for oxidation and reduction. Oxidation means that somebody loses electrons. Reduction means somebody gains electrons. And in a redox reaction, this is the third reason why a reaction takes place. The third transfer of electrons. So that is what all redox reactions are. Redox is like the big classification, like double displacement reactions. Underneath redox reactions is pretty much all the other classification reactions, like synthesis or combination, where you take two things and make one thing. The opposite of that, which is decomposition reactions, where you take one thing and you break it apart into a couple of things or more. Single replacement reactions, where you have one thing plus an ionic compound. And if this is a metal, it will come in and kick out the positive guy, and it will form a new ionic compound, and that guy will come out. You could also do this with a non-metal as well. If this is a non-metal, this guy will kick out the negative guy, and it will make this, and this guy will come out. That is because metals typically make positive charges, so when they come in, they'll kick out the positive guy, and non-metals typically make negative charges, which means when they come in, they will kick it out. But ultimately, what's happening here is actually a transfer of electrons in each cases. The person coming in this case, the A in this case, does it need to be more or less reactive than what it's replacing? Does need to be more reactive than what it's replacing. Otherwise, the reaction will not take place. So, for example, if you took like zinc and hydrochloric acid, the zinc will come in, it will kick out the hydrogen, and it will make hydrogen gas. The zinc will then combine with the chlorine to make zinc chloride, and a little balancing because it is chemistry, I suppose. There we go. And in this case, zinc is more reactive than the hydrogen. This reaction will take place. By the way, you could also write a total ionic equation for something like this. It looks something like this. I'll just go on this side, H2. And in this case, though, we actually only have one bacterial ion, which is the chlorides. And this is what is happening here, and this is what is the net ionic equation for this reaction. Looks something like this. And this does demonstrate what is actually happening in this case. It is actually a transfer of electron. Zinc is sending its electrons over. The hydrogen is picking it up, and the hydrogen has no charge here, and the zinc becomes +2 charge, and 0 and +1, right? So as things lose electrons, they typically become more positive. As things gain electrons, they become more negative. This is a redox reaction. The last type of classification is a combustion reaction. And most of the time, people think about a combustion reaction as this reaction: some organic compound that's carbon, hydrogens, and oxygens, plus O2 makes CO2 and water. Now, to be truthfully honest with you, the definition of combustion is simply you have oxygen present basically on the left-hand side. That's really all you need for it to be considered a combustion reaction. That is why, as you may be familiar with, you can classify the same reaction many different ways. So if we were looking at, say, this reaction here, a little magnesium and oxygen, speaking of burning the magnesium earlier, that is this guy right about here. And in this particular case, That is two things that make one thing, which means this can be classified as a synthesis reaction. It is also magnesium sending electrons over, which means it can also be classified as a redox reaction. And dare I say, it also has oxygen, which means it can be classified as a combustion reaction. So there are multiple ways that you could classify the same reaction. It does sort of depend on what you're looking at as to how you may classify it. But we will come across, I would say, single replacement reactions a lot in this class when we get into redox reactions. And we can talk about a whole chapter on sort of redox and electrochemistry. So again, if that's something that you're not familiar with, you might want to review some of that. We will take it from the basics, hopefully, when we get there, just to make sure everybody's on the same page. We'll go over some of the stuff that perhaps you learned in Chem 50 in terms of oxidation numbers and writing what's being oxidized and reduced and what's the oxidizing agent and that type of stuff as well. But I would say definitely in terms of the equation, the reactions, that acid-base stuff, double displacement, really big. And single replacement type reactions are really important. Again, for you to be able to predict what you get on the product side. Because in a lot of cases, you will have just the reactants sort of given to you. So you need to be able to kind of write those equations correctly. Any questions on equations, types of reactions, those type of things? Okay, then the next major thing that you should hopefully remember is our friends' solutions. Yeah. Solutions are things that typically have that aqueous symbol next to it. Solutions are a homogeneous mixture, right? And a homogeneous mixture is when you mix two things together and it mixes and looks the same throughout. There are two parts to a solution, as you may remember. There is the solute and there is the solvent. The solute is the smaller part of the solution. The solvent is the larger part of the solution, is typically what you dissolve the smaller part in. So if I had sodium chloride solid, that would be my solute. If I had some water, that would be my solvent. I put them together, my sodium chloride is going to mix together, going to give me a sodium chloride solution that gets the aqueous symbol next to it, and it again is a homogeneous mixture. How do I know what the solute is in a solution? It is the name of the solution. So if you have sodium chloride solution, sodium chloride is your solute. If you have potassium chloride is your solute. In most cases, water is the solvent, especially for ionic things, right? And polar things. It works really well. As you remember with solubility, probably the phrase like dissolves like, yes. And that means that things that are polar are soluble in things that are polar. Things that are ionic are soluble in things that are polar. Things that are nonpolar are soluble in things that are nonpolar. It's only problematic when you try to cross over polar to nonpolar, right? Those things typically do not mix. That is because they are using different types of intermolecular forces, right? Polar things typically use what type of intermolecular force? What types? Do we know what intermolecular forces are? Yeah, so dipole-dipole interaction, hydrogen bonding, right? Those are typically what polar molecules use. Nonpolar molecules use dispersion forces, right? And those are very, very different types of forces. So when you get a polar and nonpolar thing together, they're working on different ways of interacting, and they cannot really interact well with one another. So when we talk about solutions, concentration is really important. And probably the most popular concentration is molarity, right? Which is moles per liter. It is typically really moles of solute over liters of solution, right? And we could think of molarity as in a formula, right? We can solve for liters, which would be moles divided by the molarity. We could also solve for moles, which is liters times molarity. I would say we do a lot of all these three things, yes, in this class. So if it's been a bit for molarity or it wasn't your thing, I suggest you make it your thing very quickly and for this class, because we will do a lot with it. When I have my volume and I'm multiply it by my molarity, it does need to be in liters, right? Because what do you get if you take milliliters times molarity? You get moles. You do not. You get what are known as millimoles, which are like moles, but not so much. Yeah, they're about 1,000-fold difference. So if you're using molarity by itself, you should always make sure the volume's in liters so that you get moles, because probably 9 times out of 10, that is what you're looking for, moles, and you'll have the right unit. So make sure that you do it that way. Also, if you have a solution that is 4.5 molar sodium chloride. You probably also were taught perhaps to get rid of the big M when you do calculations. And I would highly recommend that as well and do the calculations more like a dimensional analysis problem. And that means that this is basically 4.5 moles of sodium chloride per liter solution. You could also use it like a conversion factor and flip it around the other way. The reason it's probably very advisable to do it as a dimensional analysis problem is I can't tell you how many people I see with the big M in their calculations and they have no clue about the volume part. They don't know where the liters is. Frankly, they don't even know there's liters. Most people just tell me moles every time they look at the big M. Yeah. So when you use both of the units, you can see both of the units and you can see what you need to do in terms of the math. So if I had 25.5 milliliters and I want to know how many moles that was, I would first need to convert my milliliters into liters, which is also a very common conversion, right? 1,000 milliliters in 1 liter. That would give me 0.0255 liters. Then if I set it up in dimensional analysis approach, I would go just opposites here again to cancel out. We would go 4.5 moles of sodium chloride per liter. Liters will cancel. We'll get you 0.0255 times 4.5 in this case, 0.115 moles of sodium chloride in this case. And again, if I want to know how many grams that would be, what would I need next? The molar mass from the periodic table, right, to get us to grams. So this is something that we do a lot. We have molarity, we have volume, sometimes we have moles, and we want to use all those three things. So it's really important to make sure that you know how to do these calculations, that you know how to calculate molarity, you know how to use the molarity, for example, and a volume to get to moles. That's really important in a lot of calculations that we do, especially when we get into that like chapter acid base chapter 14-ish or so. We do this a lot. So it's really, really important to make sure you get the right answer. Any questions on that there? Now, in addition to molarity, which is obviously really important, the other very popular thing that we do a lot with solutions is dilution. Yeah. Dilution is has a formula of M1 V1 equals M2 V2. This is before the dilution. This is after the dilution. Perhaps they teach you nowadays C1 V1 equals C2 V2. Same deal. C is just generic concentration. And that's because if you use this equation, you can use any unit of concentration. Molarity is the most common that we use, but there are other things like you probably learned percent mass to mass, percent mass to volume, percent volume to volume. So there's other units of concentration that you could use. When you do a dilution, you typically only add more solvent. And in a lot of cases, that solvent will be water, but it may not be water. You may use something else as your solvent, but water is a very common one. And because of that, if you think about molarity, which is moles of solute over liters of solution, the only thing you're really changing is the bottom number there, right? Because the solution is the solute and the solvent, which means the bottom number gets larger The molarity comes down when we do a dilution, right? Now, when we do a dilution, the moles of your solute before is equal to the moles of your solute after. Again, only the solvent changes. So this equation, though, the M1V1 equals M2V2, if you do want to leave the volume in milliliters, it's okay because it will work out as long as the volume on both sides are in milliliters. Or if you want to convert it to liters, then you can do it on both sides, but it actually will work out okay. So for example, if we look at our M2, which would be M1V1 over V2, and if our M is molarity and our V is milliliters, and we divide by milliliters, milliliters cancel, and we end up with molarity anyways. So you can leave it in milliliters if you're using this equation. If you are not using the dilution equation, you should definitely convert it to liters, as we just talked about. Otherwise, you will probably be off in terms of your calculation. Question on dilution. That is something we use a lot in a lot of places where people maybe don't think it's a dilution happening. So for example, let's say we were going to make a test tube from a table, and let's just say we had reagent 0.2 molar of A, and let's say we had 0.25 molar of B we're going to throw in there. And we'll say we'll just top it off with some deionized water. And let's say we had test tube 1, test tube 2, whatever it may be. Let's say we're going to use 5 milliliters of this guy. We'll use 4 milliliters of this guy and 1 milliliter of this guy. And we're going to throw that all into one test tube. So basically, when we do this, big test tube, we got 5 milliliters here of A in there. We're going to throw in there 4 milliliters of B, and we're going to top it with 1 milliliter of water, not drawn to scale, obviously, in this particular case. All right, so if I want to know the molarity of A in the test tube, is it 0.2 molar? What is the molarity of A in my test tube? Is it 0.2 molar? It's a 50-50 shot. That's a yes or a no. What do you think? How many people say yes? How many people say no? The third option is I don't care and I want to go home. Good, not raising your hand. I like that you almost raised your hand over there, by the way. That's good. All right, so let's talk about what we were doing here. So in this particular case, right, I am adding my A, and now I add my B in there, right? And I add my deionized water. I am doing what every time I add a reagent to the same test tube? I am actually doing a dilution. Yeah. So this is actually a dilution that's happening when you make this test tube, and the molarity of A that you put in there is no longer 0.2 molar because the volume has now changed, right? It's not just 5 milliliters of it. It's now a grand total of 10. So to get the proper molarity of A, in this case, we would use our M1 V1 equals M2 V2. Our M1 is our original concentration of A. Our V1 would be how much of it we put in there, which is 5. M2 is our new concentration after we mix it together. And V2 would be what? All these numbers added together, right? We have a grand total of 10 milliliters, I think, in this case. So when we actually put that A into this test tube, our actual molarity of it is now 0.1 molar. And that's because we have now mixed it all together, right? It's all diluted with all the water from all the other reagents that we threw in there. And that would be the same thing for B, right? If I want to know what the concentration of B would be, I would have to take the 0.25 times 4 and divide it by 10, and that would give me the concentration of B in that test tube. This is a very common thing, especially in lab, that people struggle with, like, oh, I'm actually diluting it. They think, well, it's what's on the bottle is the concentration. And it is if you don't do anything to it, right? So if you take that and just pour it in a beaker and just leave it there, that would be the concentration of it. But once you start adding more reagents to that beaker, once you add more reagents, say to a test tube, you are doing a dilution, and you have to use the dilution equation to calculate what the new molarity is in your mixture. And that is something we do a lot and people struggle with. Any questions on that there? All right, we're going to wrap it up there with